and maximizing this lambda. So here we are going to be get yi is in our data set, xi in our data set, but w transpose is only the scalar part. This is ideally going to be changed every time, right? So these are constant, these are the constant. So eventually maximizing this corresponding wi, that is the norm of the w. We just now shown, right? Norm of the w we're going to be corresponding to that. Every time it's going to be changed at the time of this algorithm is going to be run together. And what will happen somehow you will going to be get, yeah, so let's take maybe, yeah, this diagram. So what will happen somehow, eventually all the data points may not be in the right scale, or you can say right matrix at a time. You will have a data points according to x is equal to 200, and x2, you can say x1 is equal to 200, and x2 is equal to 100, and x3 is equal to very large number like 10,000. Okay, so in this case, how do you handle it with responding to x3 value? This is how somehow we can also call it as an outlier for that matter. This is very far away to whatever the actual values we have. These are some of the actual values with the same scale, with the same scale, and this is some of the different scale. So how do you arrived at that time? What will happen if you just calculating by using our distance formula? It is very far away to our distance. At this time, it may not be identified as a positive label or the negative label, but we cannot be considered this is going to be positive label or negative label. If you consider the positive label by using our calculations, so just calculating our distance by using this. So suppose this example, you're just calculating the distance of the 20 from this point to our hyperplane. If suppose I calculate all the points corresponding to the all the points, and if I just subtracted by the negative point results what we had, eventually you're going to be get as a very large number. Okay, very large number when compared to our we just predicted as normal predictions, or whenever we had large scale of the numbers we had at the same scale. In this case we are getting as very too large number, so that is the reason we have to squeeze it in, or we have to squeeze it to somehow to smooth our curve. So we have already seen how does that going to be help us as a logistic regression. It's lies between 0 comma 1. Obviously the first image we have seen, right? It slides between the 0 comma 1. Whenever we squash something or whenever we smooth something, it's going to be give as good results. That means we are going to be enter as a 0.5 results it somehow. So for that we have another function called as a sigmoid. So the sigmoid is basically looks like as a logistic curve like this. Whenever we had logistic curve, we're going to be get as a hyperplane to get maximizing the distance. Whenever you get some of the outlet like this. So for that reason, we just make some assumption to smooth our curve or squashing our curve to get this sigmoid function. The function definition as follows: 1 by 1 plus e to the power of minus x. So in this case, we just applied whatever the x we have, like y into w transpose xi. If you just substitute in our formula, you have this one, right? You have r max of w ya transpose w ya into w transpose xi. So just substitute in our x formula 1 by 1 plus e to the power of minus ya w transpose xi to just apply our sigmoid function according to that. Then you will get this formula argmax of the w, maximizing our w and according to all the data points what we had. Then what will happen if you just keep on applying it? We just call it as a logistic function, but does not mean we just normally call it as some function. The sigmoid function also we can call it as for this model. But why we need call it as a log functions? And that is also one matter. And something called as a monadic functions. You already know, right? Something called as a monadic functions is going to be, if suppose you have a function like f of x, it's going to be increasing. G of f of x is also going to be increasing. We can call it as these functions monotonic functions. And if you have a f of x, it's suppose going to be increasing or decreasing for that matter. If suppose I applied the log of f of x, it's also going to be increasing and decreasing. Whenever the f of x is going to be increasing, it's going to be increasing. Whenever f of x is going to be decreasing, it's also going to be decreasing. So similar fashion, we just applied together to reduce our minimization of the function. So currently we are using the maximization of the function. To reduce somehow the minimization of the function, we can use the log function. So you already know, right? Log, to get the differentiation of the log of differentiation of x, d by dx of log. So 1 by x, we already know about this formula, and I hope you already know about the 11th and 12th grade. So to minimize this argument of this function, you just keep applying for a monatomic function. It's always going to be helpful whenever you have logistic regression to apply. So just apply this formula together whenever you have 1 by 1 plus e to the power of minus x. All the time, it will be computed by using the 1 by x. The 1 is going to be removed and it will come on the top. That is the reason we are getting 1 plus e to the power of y minus w transpose xi. So what will happen if you have a this function, log function, along with somehow constant results, you can say. So this is the minimization, we can also call it as a cost function for that logistic regression. Then you have to reduce further, or then you can also upload, you can also minimize further by using some regularization term. So you already told about something called as an outlier. So this is our how come we are going to be compute somehow distance like 20 or 50 or 100 maybe. What will happen if you have a value around plus infinity and also the minus infinity? So you don't know that much of clarity to get the distance. Some of the points may not be concluded with somehow distance. So at this point, you can use something called as a regularization terms. So the regularization terms is going to be help us to fine tune or to just adding some of the penalty to it. Okay, adding some of the cost function penalty to it to reduce some of the distance according to the sum of the points having the positive and also the negative distances corresponding to the two different classes what we had. So the lambda is a hyperparameter tuning here and hyperparameter for the logistic curve, and the W transpose into W, we can also call it as a L2 norm for the logistic term or the regulation term we are going to be. And this is also very helpful to do something called as overfitting of our problem. So we're going to be discuss maybe in the next classes how does overfitting and underfitting going to be help us and how to avoid and what are the different techniques we have to tackle together. But as of now, you can just assume like this is also going to be helpful to reduce somehow overfitting and underfitting of the results. Yeah, so L1 norm is corresponding to that will be the same. If you use both of them, like L2 norm and also the L1 norm, we can also call it as elastic net for that matter. If you apply the law, cost function plus regularization L1 plus L2. And the basic difference between the L1 norm and the L2 norm is L1 norm create the very sparsity. I mean, the more number of the zeros when corresponding to the L2 norm. So what will happen when you apply the L1 norm? You have a data set corresponding to you have some of the features. So if you apply the L1 norm, it will identify only the most important features. It will be identify only most important features, and the very less important feature it will be considered as a zero. That means you will get more number of the zeros in the end at the end. So that's the reason we are going to be get as a very sparsity vector or sparsity matrices if you directly apply the L1 regularization. And when you apply the L2 regularization, because it has something called as lambda square in the L2 norm, so it will identically going to be get that sparsity to increase somehow. It may not be create that much of sparsity. So that is a major reason, and this is how exactly the logistic regression is going to be predicted at the end. So obviously it's going to be do with regarding the majority vote whenever we have the majority vote with corresponding to the positive label and also the negative label by using the W transpose xi. And some of the assumption obviously it's going to be linearly separable. If it is not a linear separator, you can add all the things like mathematical terms and everything. But this is a theoretical machine learning. You cannot be get it from in a scikit-learn. You directly use the function and call it for some of the parameters. You just directly calibrate the results. And you can also interpret by using the weight vector. That is also very helpful to fine tune that. And the space